Okay, so let me give you an outline of the solution. In, say, region 2, plus, how to find the energy eigenvalues. Okay. Now, it turns out that it's actually very hard to find the exact solution to this. I would even venture to say it might actually be easy. So it's actually easier to do because you have to solve a transcendental equation, okay? So that's why it's hard to write. There is no very clean closed form expression for the energy eigenvalue. So let me just show how you derive this. So let me just reparameterize the problem slightly. So this is my V, and this is the well. Now let's call the size of the box, instead of L, let's call it A. Okay, so this is A. And this is X, so I am, what I'm doing is that I'm making the well to be minus V naught deep, where V naught is a positive number. Okay, so our potential is V of X is 0 for X less than or equal to or less than 0. It's minus V naught for X between A and 0, and it's 0 for X greater than A. Okay? So now we know that the form of the solution is going to be some e to the power k, 1 of x. So here, the coefficient, I set it to 1 because I can always, we know that only the relative values of the coefficients matter, because at the end of the day, since we have to normalize the wave function, we have a freedom in choosing one of the constants. And that I've used up that freedom to set that to 1. And then, so this is in region 1, region 1. In region 2, we are going to have the sinusoidal solution, e to the power I k of x plus b e to the power minus k of x. So here, AB doesn't have anything to do with AB that we chose above. So C is e to the power minus k1 of x. So this is in region 2, and this is in region 3. Okay, so this is region 1, 2, and 3. Okay. Okay. Any questions? Let me just remind you what K1 and K are. K1 is minus 2m of E. Actually, K1 is, it's the other way around here. I made a mistake in my notes. So K1 is 2m E this is actually V naught minus E, right? Square root by H bar. And K is, the total energy is negative, right? So we are going to write this as minus 2me square root of H bar. Okay? Okay. So now we impose the continuity condition. So one thing I wanted to say about quantum mechanics is that, what we're doing here, we are just solving a real Schrodinger equation, right? Because it's the time-independent Schrodinger equation, and it's completely real, right? So we are actually solving a quote-unquote a classical differential equation. The only thing that's giving rise to the so-called quantization stuff here is the fact that the boundary conditions related to the wave functions being normalized, right? And having this continuity condition across the boundaries. Okay? So apart from that, I mean, physically it means something very different, but we are just solving differential equations here. Okay. So what are the boundary conditions? Boundary conditions are the wave function psi must be continuous across the boundaries, continuous and I would say differentiable. Across the boundaries. A better word to use here would be kind of a smooth. And the other one is psi prime is also continuous across the boundaries. Okay? Right. So how many conditions do we get if I impose these two conditions? Can someone tell me?
Seems like 3.
Can you explain how?
I mean, smoothness seems to be 2 conditions, continuous and differentiable.
Okay. Actually, let's just call, let's just keep, yeah, the smoothness is actually something that just kind of comes out. So this is just continuous is enough, because the smoothness is something that just is a consequence of having a potential that is that has a finite discontinuity, right? So it's not something that we have to actually impose. So if I were to ask you, let's just ask the wave function being continuous across the boundaries and the first derivative of the wave function being continuous across the boundaries, how many conditions do we have? How many boundaries do we have? We have 2 boundaries, right? Right, between region 1 and 2 and one between 2 and 3, right?
Yes, sir.
So in region from the first one, from number 1, we will get 2 boundary conditions, and from the second one we have 2 more, right? So we get 4 boundary conditions. But we have 3 quote unquote three parameters, right? 3 constants. So that means that A, B, and C. So this is why K is quantized, okay? Because to actually, you cannot actually fit all these constants, including K. So if you had like A, B, C, and D, then you would not need to quantize K, right? So, if you have 4 boundary conditions, and so it's kind of an overdetermined system. So that means that you're not, you're kind of you're not guaranteed solutions. You're only guaranteed solutions for some special conditions. And you will see that there's actually, I think that there's actually a smallest value of V naught for which you can have bound states. Okay. So there are, potential wells which are, if they're not deep enough, then you cannot have a bound state. Okay. Let's see if we can derive that. Okay, so this is kind of hand wavy. So what are these conditions? Well, the first one, if you look at, is just 1 is equals to A plus B. Okay, where did that come from? Let me just. It's just yeah. So it's when e to the power k1x is equal to a e to the power I kx plus b e to the power minus I kx, and you put x equals to 0. You get this equation, right? So this is our first boundary condition, is 1 is equal to a plus b. Okay, now if I take its derivative and set that boundary condition on the left-hand side, I'll get k1 coming down. On the right-hand side, I'll get I of k, and then I'll get a minus b. And then we have, from the other boundary, we have c e to the power, e to the power minus k1x is a e to the power I k of a plus b e to the power minus I k a. So this is not as nice as the other one. Okay, so what did I do wrong here? I should have had an a here, right? Okay. And then if I take the derivative, it's minus k1c e to the power minus I, it's not I, k1 of a, I of k, the derivative, a e to the power I k a minus b e to the power minus I k a, okay? So these are the solutions. So, you have 4 equations. You can easily get rid of A, B, and C. So if you get rid of A, B, and C, as promised before, you will get a relationship between K and K1. So you get a constraint on the energies, right? And that equation you can derive. Now I can derive that equation. And that's going to be given by 2 cotangent of Ka is equal to K by K1 minus K1 by K. So, K and K1, they, if I give you a potential well, you have A fixed, right? A is fixed. And V0 is fixed, right? So this guy is fixed. And so the only thing that is not fixed is E. E solves this equation. right? Or the solution of this equation gives you E. Okay, so that's basically if we can solve this. But of course, as you can see in the left-hand side is a circular function or some trigonometric function, and the right-hand side has is some kind of it's not a circle function, it's some polynomial or something, right? Or it has square roots or something like that. So the idea is that this is not a nice equation. It's what is known as a transcendental equation, and the way we solve this equation is graphically.